Today, we want to talk about how much more substitution can there be? Because it's just more substitution. After we do parts, we're going to wheel back around and come back to substitution because there's even more of it. It's not because most integrals can be integrated through substitution. The reason that I care about this so much, the reason that I keep looking at these substitution problems is that it's a useful technique, not just for integrating functions, but for solving math problems in general. It's an idea, the idea is switching from one set of variables that are inconvenient to a convenient set of variables. That's what it's about. Think back to elementary algebra and solving linear systems, solving two equations and two unknowns, finding out where two lines intersect. We can draw a graph. That's important because we'll understand what's going on. And the other technique is substitution. We take one of the equations, solve for one of the variables, and plug it into the other equation. We take our system of two equations with two variables, combine them into one equation with one variable. We took a new problem, where do these lines cross, and compared it to a familiar problem. Where does this one line cross the x-axis? We simplified the problem. And that's what we're doing here. We're taking these messy integrals and trying to make simpler integrals. Here's the important question. We've got powers of sine and cosine, powers of secants and tangents. We've got all of our possible substitutions. If w is sine, then I need one factor of cosine to be the dw. Any other factors of cosine can be converted into sines in pairs. I should have written this under this one. I don't know why I sent it anyway. Oh, that's right, because I went horizontal on these and I couldn't fit those on the other side. So I just wrote them. If we make the substitution w equals cosine, here's what we need. We need one factor of sine to be the dw, and then any leftover sines can be converted into cosines. The important thing here that we notice is that the leftover sines only convert to cosines in pairs. So that tells us something about m and n if we want to make the substitution cosine. If w is going to be cosine, I need one factor of sine to be the dw, and I need an even number of sines to convert to cosines without introducing radicals. If we want to do the cosine substitution, I need an odd power of sine. If we want to do the sine substitution, I need one factor of cosine to be the dw, and I need an even number of cosines to convert to sine. If we want to make the substitution w equals sine x, we need an odd power of cosine. One to hold on to be the dw. The even ones can convert to sine without introducing radicals. Secant and tangent changes the game a little bit. Because if we want to make w equals tangent, then dw is secant squared. I need an even number of secants to be the dw. So that changes the game a little bit. If I have some tangents and an even number of secants, then I can make the tangent substitute. Or I can't remember where that sentence started. It happened in 5 seconds. And my memory doesn't last that long. If we want to make the substitution tangent, I need to have an even number of secants. 2 to be the dw, and any other secants I can convert into tangents, since secant squared is tangent squared plus 1. And secant's kind of the weird one. If I want to make the substitution w equals secant, I got to save one factor of secant and one factor of tangent to be the dw. Then I have to have an even number of tangents left over to convert into secants. So the ones down here are how we get to the w. that we decided on. So we save some to be the DW, we convert the rest. I want W equals tangent, I save some secants to be the DW, I convert the remaining secants. That tells you what the powers have to look like to make these substitutions. Any questions? Here's the question for this problem. Which integrals of this format, powers of sine and cosine, or powers of secant and tangent, are not substitution problems? Which of these integrals are not substitution problems? Up here, down here. So this is the question that I want you thinking about over the weekend. No, it's Thursday, but I'm giving you a 3-day weekend to solve this problem. Which of these integrals, that is values of m and n, are not substitution problems? Let's begin with m and n integers. Let's limit your scope. I want you to start with the non-negative integers. And I want you to figure out which of these integrals are not substitution problems. So it's going to take some experimentation. Notice that I said non-negative integers. I didn't say positive integers because 0 is on the table and 0 is not positive. Because yesterday we did one cosine to the 5th. And we saw that cosine to the 5th, the substitution play was actually to go with sine. Because we had 5 cosines. One of them can be the DW. The other 4 can be converted into sines because there was an even number left over. So because it was a cosine to the 5th, the substitution move was sine. If I had sine to the 5th, our substitution would be cosine. If I had sine to the 5th and cosine to the 3rd, then we have a choice. Good news, we have a choice. Either one will work. One sine, the others can be cosines, or one cosine, the others can be sine. If they're both odd, no problem, we can choose. Of course, then at that point, we have to choose. My choice, if it doesn't matter, if m and n are both odd, your move should be to go with sine because you don't want to introduce negatives if you can avoid it. Avoid sine plus or minus errors. So go with sine, S-I-N-E. I haven't really done a lot of problems with secants and tangents, so that's where the question is. Which of these integrals, the values of m and n, are not substitution problems? Maybe I'll post up a discussion in Canvas. Now, one way to go about that, included in this problem, or in this question, is also the alternate question, which ones are substitutions? So this is the thing that I want you thinking about and working on. What you want to try to do is try to find a way to summarize your observations about powers of sines and cosines and powers of secants and tangents. Here's the way that this is going to work. This is going to show up this setup. Yeah, I'm going to type up a version of this setup, and it'll go up as a graded discussion on Canvas. To succeed in the graded discussion, you just have to post something. You have to find something that will work. It could just be like, oh, hey, I found this integral. Here's what I did, and it worked. And then you get points. I would encourage you to look at other people's results and see if people are, if you notice anything in all the results that people are posting, and then just respond to those. So it's a graded discussion. You just have to post one time with one contribution, and then all will be, then you get the points. Any questions? I don't want you thinking about it. Take a look at the integrals that people are finding that are substitution problems. Take a look at the integrals that people are finding that aren't substitution problems. And see if you could look for patterns. One of us might not be able to see all the patterns, but all of us will probably see the patterns and find a way to describe it. Okay, one of y'all might not be able to see the patterns because I actually know what I'm looking for. So that would be cheating. Any questions? It's going to require experimentation. Math experimentation, our favorite kind. Remember that show Mythbusters? Most of the questions on Mythbusters can be solved with math. You could just do calculations and say, no, that's not going to how it works because math. But that would make for an awful television show. Actually, I kind of watch a YouTube show that is people doing math. It's called Numberphile. It's a great channel. You should check it out. Numberphile, all one word with a PH. Not as in file, but as in file. I like that. No one would watch a show if you do the math explaining why you don't have to blow stuff up. People will watch a show if you blow stuff up. Any questions? Yes.
So like for the discussion or answer, should we like show our work and like take a picture of?
I think in discussions you can post pictures. You can also practice. So if you can post pictures in discussions, then you can do that. If not, you should be able to post pictures. I will try to make that happen if it doesn't by default. Or you can practice typing stuff. There's an equation editor. So you can practice typing on the equation editor and then learn how to type stuff in math. It is super frustrating and annoying because you're trying to type math and there's superscripts and subscripts. And you're talking to a computer and computers are super dumb. Computers are like, I don't know what you're trying to tell me. They can calculate the crap out of anything, but they aren't very smart. So that's what I want to know. Under what conditions? Ultimately, the goal is under what conditions are these integrals not substitution problems? We're going to find that out by deciding on what conditions these are substitution problems. Any other questions? All right. If you would recall, we integrated some integrals. This is one of our base model integrals. The integral of 1 over x squared plus 1 is arctangent x. I think this book listed as arc x squared plus 1 in the denominator. And I was raised saying 1 plus x squared because I write my polynomials constant up. But I don't know where I picked up this x squared plus 1 stuff. So we had some integrals. There was one that we did with substitution. This first one, basic integral, everybody just knows this one. This is one that you know. This is a calculus, one of the calculus entries in the multiplication table. You know this just like you know 7 times 8 is 50 something. So this is just something that you just have to remember now. The amount of things that you have to remember as you go through your mathematical career just grows and grows and grows. And you don't get to forget any of it. I don't see why math is so hard. You have to remember everything all the time in perfect detail. Okay, I can see why people might be intimidated. This integral, x over x squared plus 1, that one we did with substitution. We said w is equal to x squared plus 1. dw is 2x dx. So this x dx had to combine them, even though they look like they're in different places, but it's all just multiplied together. The x and the dx became a 1/2 dw. That's where the 1/2 came from. And we're integrating the function something 1 over x squared plus 1. So 1 over w, and that's my natural log. So this was done with substitution. And then dw is 2x to x. We divided out the 2 because it's a constant. So 1/2 dw is x to x. And our function that we are actually integrating is 1 over w. It's important to see where things come from. Helps solidify the process in our minds. Helps us remember things. This is slowly sliding down. There we go. And then at one point, I introduced a couple of integrals for us to think about. The integral, I put down here an x to the 4th plus 1. And I made the claim that these are both substitution problems. And so the question was, what are the substitutions that we should make? So I actually think about this question. It was 2 days ago. Yesterday, you were hoping I forgot about it, but I did not. I just got distracted by this products, powers, and trig functions because I wanted that sitting in the back of your mind. So the question has come due today. These are both substitution problems. The question is, what is the substitution for each problem? What are we going to make w? What do you suggest for w in this first integral, x cubed over x to the 4th plus 1? What do you want your w to be? What can it be? Remember, it's a choice that we make at the beginning. Then we have to see if our choice is going to work by figuring out what dw should be. And then once we do that, we've got to decide what our function that we're actually going to be integrating is. 3 choices to make, or 3 things to find out. Any suggestions for a substitution for x cubed over x to the 4th plus 1? What do you suggest? Just x to the fourth? That was a leading question. I get to do that. This is not a court of law. Here's one way that we might go after this problem. Why would you suggest x to the fourth? What makes x to the fourth a candidate, or x to the fourth plus one? What makes that a good candidate for substitution? Its derivative is mostly there. Perfect. That's exactly why x to the fourth, or the x to the fourth plus one, would make good substitutions for this. It makes sense to try to choose this x to the fourth part because the derivative is mostly there. If we use an x to the fourth or an x to the fourth plus one, then the derivative is 4x to the third. We're off by a constant, but we know we don't have to care about that 4. I will suggest that if you're going to make a substitution, if you can pull the constant term in, that might be a good idea, because that's going to take this x to the fourth plus 1 and make that those two terms one term. So that works. That's a good idea. I like it. So my suggestion would be x to the fourth, but that would give us a w plus 1 in the denominator. We saw problems where that was inconvenient, but the rest is just plus 1. So I like that. Then dw can be 4x to the third. We're going to turn this around. We'll get rid of that 4 and go 1/4 dw is x to the third dx. And this shows us the function that we're actually integrating. It's a 1/w function. Let's take a moment and be unsure of ourselves. We're students. It should be easy for us to be unsure of ourselves. And let's say, teacher ain't looking. Let's ask our friend, Wolfram Alpha. If you haven't heard of Wolfram Alpha, congratulations on getting this far in math and not having seen Wolfram Alpha. If you're pretending like Wolfram Alpha doesn't exist because some teachers are trying to hide it from you, I don't know, keep playing along. They're still teachers, right? But I want you to know about Wolfram Alpha. If you have not heard of Wolfram Alpha, get thee unto a browser and find Wolfram Alpha. And what I'm going to do is I'm just going to take the function that we're concerned about, x cubed over x to the fourth plus 1. And I think, hey, Wolfram Alpha, what do you think of this function? Hopefully it won't time out on me. There we go. There's what I'm looking at. There's a graph. There's a more detailed graph. Oh, partial fractions, 0. Ooh, series expansion. What's all this stuff? Oh, there's something that's familiar, the derivative. Oh, dang, the derivative. X cubed over x to the fourth plus 1. Looks like they use the quotient rule. That looks familiar. And here's something we might be interested in, the indefinite integral. This is exactly what we're looking for. And look at what the integral has. 1/2 log. When Wolfram Alpha says log, it means natural log. Your calculator, like your TI-84 says log, it's log base 10. That's because your calculators are kind of old and outdated. Even though we call log base 10 the common log, the natural log is way more common than the common log, so we just start writing log. And this answer fits with exactly the substitution that we made. Because what's the function that we're going to be integrating here is 1/w. Integral of 1/w is natural log of w. The 1/4 is from the 4x cubed being rearranged to get the x cubed dx. And it's just x to the fourth plus 1 in parentheses, because that's always going to be positive. Oh, cool. I don't know what step-by-step solution for us. Wow. Here's what I don't like about Wolfram Alpha. I make my substitutions W, and Wolfram Alpha uses the traditional U. This is why when you look for W substitutions on Dr. YouTube, all you find is U substitutions, because U is way more common. My method of using W is twice as good. It's like literally twice as good. W. Weak ass U substitutions. No. W substitutions. It's like that's how you get more power. Like forget one exhaust, dual exhaust. That is the way, right? That's how you make it look like a sports car. Dual exhausts. Even though it's an inline 4 engine, all the exhaust is coming out on one side, and eventually you just split it. It's just the one big pipe going out the back, but they're like, oh, no. You know what looks cool? 2. So let's overcomplicate things just to look cool, which when you're dealing with cars is the correct answer. You overcomplicate things to make the car look cool. And then people try to make arguments like, oh, no. All the exhaust is coming out on one side of the engine. At the very end, they're like, oh, no, make 2. And that's it. That's how it happens. And you're like, oh, no, but I have a Subaru and the exhaust goes out both sides. I'm like, oh, look under the car. You know, because you replaced the exhaust, because I can hear you from 40 miles away. Because I live within 40 miles of a friggin' on-ramp. And so you're like, oh, on-ramp, exhaust. You know what I mean? Some of you know exactly what I mean. Because I've heard some of you driving your friggin' cars. My car did it too, so I'm not trying to single you out. But if you look under there, it does come out, the exhaust comes out both sides of the engines, and then what does it do? Goes into one pipe and then to the back of the car. But they're like, oh, no, it's gotta look cool. So they go back out. Like, oh, dude, just make the 2 go right up. Now manufacturers have really figured it out, because they'll have fake exhausts. If you see a Ford Explorer ST, I don't know who finds these things, but if you see one, it has these big old exhausts on the back, look under that. That's not where the exhaust comes out. That's just a can pretty much bolted onto the bumper. The exhaust is like coming out pipe behind that, and it's pointed down. But we all know that big exhaust pipes look cool, so there it is. Anyway, what are we talking about? Oh, yes. W is a much better substitution. But if you want to go with like the U substitution, like all those Brittany and Justin wannabes, then so be it. So great, this is a substitution that's going to work. Look at all the stuff that they went into making this decision. We wanted to look for something that was the derivative, and something to make the that we can substitute. But the key driving factor in what we're going to make the substitution, what we're going to call W, is what's going to be the DW, just like it was at the top of the page. When we're looking at cosine to the 5th, we didn't start by looking at what the substitution should be. What should W be? We said, what can be the DW? That's what was driving the decision. What's my DW? So with that in mind, can anybody think of a substitution that we could do on this x over x to the 4th plus 1? Anyone have any ideas? Because I know someone that has some ideas. So I wonder what ideas someone might have. So if we scroll down, if we just take a look at this, Remember, getting the answer is almost never the point in a math class. If all you're going to do is like write this down and not take anything from, not look at why this answer might be the case, then I don't even know what you're doing here. You don't want to learn math. You just want certification, which means you just need more money. If you had enough money, you don't have to go to school. You can just buy yourself a degree. And if you have enough money, you just buy yourself a degree from a fancy school like Harvard. Here's how I know that none of you have enough money to bribe me for a better grade. You're here. If you had enough money to bribe me for a better grade, we'd all be at Harvard, at Harvard. Then it wouldn't be a bribe. It would be a contribution to the scholarship fund. I'm here. Don't sue me, Harvard. I'm just joking. What if I went after Stanford? Would that be cool? All right, I'll go after Stanford. Berkeley is a little different. It's a public school, but if you transfer to Berkeley as an undergrad, you need to know they don't care about you. You're not a graduate student. You're just an undergrad. It might be, it's going to be a big deal to you, but the school's like, oh, whatever. They're just undergrads. If a big battle happened, you were going to be standing on the front line as an undergrad. What are we talking about? Oh, yes. Let's take a look at what this tells us and then see how that matches with our thinking about how to make decisions about substitution. The answer turns out to be an arctangent of x squared. That right there is telling us what our substitution should be. It looks like our substitution should be the x squared. Does an x squared substitution make sense in this problem? And why does an x squared substitution make sense in this problem? Because the derivative is sitting right there in the numerator. It makes sense to make the substitution x squared because the x can be the dw. So clearly, working backwards, it looks like this is what happened. Notice that I can only grab the x squared, not the x squared plus 1, because I can't separate out an x squared plus 1. But if w is equal to x squared, that works because I can say dw is 2x dx. That will get, we get rid of the 1/2. And so a half of dw is our x dx. And we have that. Moreover, when we ask our friend Wolfram Alpha, we can see that 1/2 sitting right out in front. Now our integral was an arctangent. So we must have been integrating a 1 over something squared plus 1. And if we replace the x to the 4th with an x squared squared, if I just read this as there's my w being squared plus 1. The x in the numerator is going to be contributing to the 1/2 dw. And the function that we're integrating, the outside function, is going to be 1 over w squared plus 1. And the integral of 1 over w squared plus 1 is arctangent w. We have teamed up with Wolfram Alpha to get the substitution on this problem. But we didn't just grind out the answer or look up the answer. We saw that looked at the answer and saw how it how to help us make decisions about what the substitution should be. That was the point of the exercise. Looking at it's so boring. My phone is falling asleep. Fall asleep all the time in math class. I'm like, I'll wake up, phone. If you fall asleep in class, I'll only wake you up if you're snoring. If you fall asleep in class, it probably means that you need sleep. And so I'll just let you do that. You know what I mean? And then when you wake up, if we can all successfully sneak out the room and turn the lights off. That would be most fun. But when you wake up, you think, man, I should have just slept in. I missed class anyway. What are we talking about? Oh, yes. So by looking at the answer, we can see how these decisions how we make these decisions. The question becomes, how am I going to recognize this just in general? You're going to see things like this, have to look up the answer, and then you'll start seeing these patterns. All you have to do is thousands of problems, and it'll get easier. I know we don't have a lot of time for thousands of problems. But a lot of times in math class, the question comes up, how will I know that this is what I'm supposed to do? The answer is, with experience, you'll just know. All you have to do is spend time to get experience, and then you start recognizing things. Isn't it cool? I think so. Substitution is great. And it's not just for integrals. Any questions? Comments? Snide remarks? I can't believe I recorded that whole dual exhaust thing. I should edit that out, but I don't edit videos because editing videos is a really annoying thing to do. So your task from the beginning of class, which of these integrals are substitution problems? Which of these integrals are not substitution problems? Try to find nice ways to describe what's going on. You want the simplest form possible. Chances are we're going to come up with a lot of observations. So once we start generating more observations, try to come up with the simplest observations possible. I'm not going to tell you how many we're going to need to describe this. So we're just going to see what we come up with. All right, that's going to do it for today. Start thinking about this problem. I'll see you all on tomorrow. Everyone have a good day. And thanks for playing.